Last class we learned about the definitions of all of the trig functions. So we have the values of x and y and r and how they're related to the different trig functions. We also started to mention how there are reciprocal functions of each other. So all we did when we needed to take cosecant was flip over the fraction for sine. When we needed to take secant, flip over the fraction for cosine. Cotangent, flip over tangent. Which is great, but what it also allows us to do is have these 6 reciprocal identities that we're going to use throughout this class. This would also be like one of those little charts that I'd write down, so I'm going to pause and give you a second here for us to write down these 6 reciprocal identities for the 6 trig functions. So the reciprocal identities, again, are how we can relate the pairs, in my mind, of trig functions together. So sine and cosecant go together. They are reciprocals of each other. So if you had the fraction for sine, you could flip it over to make the fraction for cosecant. And if you have cosecant, you can flip it over for sine. Cosine and secant, same relationship. Tangent and cotangent, same relationship. To help you try to remember this, each of the pairings only has one co. Sine doesn't have the word co in it, so it goes with cosecant. Cosine already says co, so it goes with secant. Tangent and cotangent are pretty obvious that they go together. That's just how I've always remembered it. But knowing these different reciprocal identities will allow us to very quickly answer some different kinds of trig questions. Like say, for instance, we're asked to give cosine of theta given that secant of theta is 5/3. Instead of having to go through and figure out with x, y, and r from one of the reciprocal values here, from r being 5 and x being 3, we can remember that cosine and secant are reciprocals. And since they're reciprocals, that means that all we have to do to find cosine of theta is flip over the ratio that stands for secant of theta. So we didn't have to go through the whole pizzazz of figuring out x, y, and r.
This is cosine and
secant. Secant. Yes. Yes. If we have a second example here, it says find sine of theta given that cosecant of theta is negative square root 12 over 2. Again, our brains should start to remember that sine and cosecant are reciprocals. That's how they're related, which means I would just need to flip this fraction over. So if I go to do that, and this one's going to get a little bit more complicated just because of the way that it is. If we flip over sine of theta, that's going to end up being negative 2 over square root 12. Is anybody's spidey senses going off about this answer? What's happening? Square root is in the denominator. Uh-oh, we got to fix it. How do we fix this? What was the trick I told you last time? What do you move to the top? Just 12? Square root 12? Okay, so it's 2 square root 12, and what stays in the bottom? 12. Now, for multiple reasons, we're not finished with this answer just yet. Does anyone see one of the 2 reasons why we're not finished yet? If we were always trying to give simplest answers. Can you reduce 2 over 12? Yeah, what is 2 over 12 reduced to? 1 over 6. So this really becomes square root 12 over 6. Now this next one you might not see, but there's still something wrong with this answer. Just describe it to me then. Absolutely. My friends, 12 can break down into 2 times 6 and 2 times 3, which means that we can take out this pair of 2's and be left with the 3 underneath the square root. So this becomes 2 square root 3 over 6, and then wouldn't you know it, 2 and 6 are the outside numbers. We can reduce that again. This ends up becoming square root of 3 over 3. So two things we realized with this question. Number one, when we started, if we had noticed that this number was not in simplest form, we could have already done the simplest form to begin with, because we always should be writing our radicals in simplest form. But when we flip our fraction, if we put a radical in the denominator, we have to rationalize that denominator and simplify as much as possible until it's simplified as far as we can. Now there's some tricks of the trade here when it comes to making sure that your trig values have the right sign, because I dropped a negative here anyways. Hello, these should all be negative. I'm so sorry. But that's a great point. I didn't even mean to prove that point. There is a pattern to which trig functions, of the 6 trig functions, are positive in particular quadrants. So when we are looking at all 4 quadrants, we have an acronym that we can use to help us know which trig functions are positive in which quadrant. Does anybody who's taken my class or is in calculus remember that acronym? All students take calculus or all-star trig class, which is what this is. This is an all-star trig class. Look at you guys go. In quadrant 1, which has an A in it, we are saying that all of the trig functions are positive. So sine, cosine, tangent, cosecant, secant, and cotangent are all positive values. You should not answer with a negative fraction when the angle that we are looking at is in quadrant 1. If we go to quadrant 2, that says S. That means that the only trig functions that are positive are sine and its reciprocal cosecant, because of the S right here in sine. If that's the case, what can we conclude about the T quadrant, the 3rd quadrant? Tangent and what else? Tangent and cotangent. So tangent and its reciprocal are the only ones that are positive. Everything else would be negative. And then last but not least, what about the 4th quadrant? Cosine and its reciprocal, which is secant, are the only 2 trig functions that are positive. The rest of them will be negative. So remembering the ASTC, All-Star Trig class, or All Students Take Calculus, however you want to remember, I had a student probably 4 or 5 years ago that said that this acronym should be All Sad Turtles Cry. Sure, as long as you remember it. All Students Take Calculus or All-Star Trig class will help us remember what is positive where, so that you can answer questions like this. This question, this example 2, wants us to determine the signs of the trigonometric functions of an angle in standard position with the given measure. So we want to know what quadrant this angle lies in. So if I draw myself like a cute little coordinate grid, where would I put the angle of 87 degrees? What quadrant? Yeah, the first one. Because 87 degrees is going to look something like this, correct? So which trig functions are positive? All of them. So all trig functions in this quadrant would be positive. We could list all 6 of them out, but I'm sure you don't want to do that. So we would just say all of them are positive. If we draw 300 degrees, what quadrant would 300 degrees lie in? The C, the 4th quadrant. Because if we think about like our quadrantial angles, this is 90, 180, 270, 360. So 300 is larger than 270, but not quite as big as 360, which means 300 degrees would be somewhere here. And in that quadrant, what are the only 2 trig functions that are positive? Cosine and secant. So we would say that sine is negative, cosine is positive, tangent is negative, cosecant is negative, secant is positive, and cotangent is negative. The only 2 that are positive are cosine and its reciprocal. See how this is working? Now what if I give you a negative angle? I want you to tell me all the same things about negative 200 degrees. What quadrant would negative 200 degrees be in? So if this is 0, this would be negative 90, negative 180, negative 270. So where's 200? Oh, it's in that second quadrant. It's just going this direction because it's negative 200 degrees. In which case, what are the only two trig functions that are positive? Sine and cosecant. Yeah, still working on pronouncing them, I get it. Cosecant. Going a little bit further, knowing these four quadrants and which one's positive where will actually help me be able to place angles when we're given different pieces of information. Yes, yes. For example, let's say I was asked to identify the quadrant or possible quadrants of an angle theta that satisfies the given conditions. So we want to know the quadrant where sine of theta would be greater than 0 and tangent of theta would be less than 0. So here's how I've always done this one is I'm going to draw myself a coordinate grid and I'm going to put A, S, T, C because I want to make sure I remember which are going to be positive where. If we know that sine of theta has to be positive, which two quadrants is sine of theta positive in? S and A. So what I'm going to do is I'm going to circle those. Those are two options because that's where sine is positive. But I also want tangent to be negative because it says tangent of theta should be less than 0. So which two quadrants will tangent be negative? These two, right? So if I circle those two, all I'm looking for now out of this work is where my two options overlap. So if I know that sine has to be positive but tangent has to be negative, which quadrant should I be in? Quadrant 2. That's where the overlap is. Because tangent is positive in the A and the T quadrant, which means it's negative in the S and the C quadrant. Let's look at another one. Maybe this time it says cosine of theta has to be less than 0 and secant of theta has to be less than 0. Okay, I'm going to draw my work because I think it's super helpful to have A, S, T, and C. Cosine has to be less than 0. What are the two quadrants where cosine is less than 0? T and S, so we circle those. And then, secant. Secant is one of the reciprocal values, and since those aren't listed in ASTC, let's think for a second. Secant of theta, what is that the reciprocal of? Secant of theta is equal to the reciprocal of cosine of theta. So really, I've been given more information about cosine. Secant of theta is less than 0 in the same two quadrants. So we weren't able in this question to get it down to one option because we were given information essentially about the same ratio, one of them being the reciprocal of the other. So we'd give two options. We would say either quadrant 2 or quadrant 3. We would need one more piece of information to be able to tell exactly what quadrant this angle would be in. We got another table here that I do want you to have written down because I think it's very helpful, but it has the ranges of the trigonometric functions. These ranges will make more sense when we're in chapter 4 and looking at the graphs of these functions, but I do need you to know the ranges of the trig functions because there's an opportunity that we would have impossible or possible questions for you, meaning I might ask you, can the sine of theta be equal to 100? And if I had an equation that said sine of theta equal to 100, is 100 between negative 1 and 1? No, so we'd have to be like, that's impossible. It can't be equal to 100. So we'd have to throw that question away and say it's impossible. So it's important to know the ranges of these functions. Since they're reciprocals of each other, and again, this will make more sense when we graph these functions, they are like bowls of each other. So between -1 and 1, it makes like a little circle. The other one is saying outside of -1 and 1. I'll give you a chance to write that down. So a question you may get in regards to the ranges of trig functions for at least this chapter, until we get to the graphing chapter, is to decide whether each statement is possible or impossible. And again, the first one I'm asking you is sine of theta equal to 2.5. Is 2.5 in the range of outputs for this function? No. So we would say that this one is impossible. There's literally no angle that I could give you where the sine of that angle would be 2.5. So that's an impossible statement. What about tangent of theta equal to 110.47? Is 110.47 in the range of outputs for tangent? Yep. Yes, because tangent, its range is from -infinity to infinity. So it literally doesn't matter what you ask. The answer is going to be yes. This one is possible. Okay, in the real number system. Anything you ask in the real number system will be possible. Good point. And then we have a question like this. Secant of theta equal to 0.6. Is 0.6 in the range of secant of theta? Because the secant of theta says it should be smaller than -1 or bigger than 1. Is 0.6 smaller than -1 or bigger than 1? So this one is actually impossible. Secant of theta has to be outside of -1 to 1. And so why do we start to teach all of these things, and why do we know them? One, it's good to always be able to qualify your work, make sure things are possible and not crazy. But also, we can start asking you questions that sound like the questions we did last class, but are actually a little bit harder. This one, example 5, this is the last example for today, says, suppose that angle theta is in quadrant 2 and sine of theta equals to 2/3. Find the values of the 5 remaining trig functions. Last class when we did this, I gave you a coordinate point. That coordinate point allowed us to put it on a graph so we could find the x, the y, and the r that make the triangle and help us write all of our trig functions. This time I don't give you a coordinate point. Instead, we have this information. Here's the things I know immediately. Number 1, I know that the angle theta is in quadrant 2. In quadrant 2, which of my trig functions should be positive? Sine and its reciprocal. Everything else we know has to be negative. So if all else fails, at the very end, you pop a negative in front of everything else except for sine and its reciprocal. We also know that sine of theta is equal to 2/3. Well, my friends, if sine of theta is equal to 2/3, we know based on the definition of sine that this is y and this is r. Because the definition of sine is y over r. Which means we can do the following. We know that y is 2 and r is 3. We need to find the value of x. Last class we learned that these three things, x, y, and r, were related by what? Say again? Pythagorean theorem, where x squared plus y squared equal to r squared. And we were able to just quickly do the square root of x squared plus y squared because that was solving for r. But we're not solving for r this time. What are we solving for? X. So if we solve this equation for x, it's going to end up being r squared minus y squared, and then taking the square root of that. So this time we do r squared minus y squared, and we can find the value of x. If we find the value of x, so here I go. I'm going to do the square root of 3 squared minus 2 squared. 3 squared is 9, 2 squared is 4. We get square root of 5 because I can't take the square root of 5. However, which of my trig functions should be positive again? Only sine, which means there has to be some way I make the other ones negative. because this is in quadrant 2 and we're going in a negative horizontal direction, this whole time the x should actually be negative. This is the only way I can get my other trig functions to be negative is if the x value is a negative value. And that's what we learned from that function being in quadrant 2. Sorry, the angle being in quadrant 2. Is that there has to be a negative somewhere and it comes from the x. Which means we can find all of our trig functions very quickly, putting these together. Bless you. So sine of theta we already have, which was 2/3. We can do cosine of theta, which is negative square root 5 over 3. We can do tangent of theta, which is 2 over negative square root 5, but I'll rationalize that denominator to negative 2 square root 5 over 5. And then all I have to do is the reciprocals. The reciprocal of sine is cosecant, which is 3 over 2. The reciprocal of cosine is secant, so that's negative 3 over square root 5, but I'll rationalize that denominator. And the reciprocal of tangent is cotangent, and so I flip the original fraction over. Again, notice the only trig functions that are positive here are sine and cosecant. We have successfully put a negative in front of all of the rest of our trig function values, confirming that this is in quadrant 2.